Hi everyone, hope everybody's enjoying their summer. In this video I plan on going over some of the content that you can find in your summer work. For reference, I'm going to start off by going over the math review packet, and then I'll do some of the physics review stuff. My goal is not to go over everything, but just to jump around and go over a few of the problems that I think you guys would benefit from. So what I'm going to do is we're going to start off with the math review, and part 1 deals with solving equations. I tried to emphasize that first year, but we will make use of this skill much more this year. So just to start off, if you look at problem number 1 on the very front page, you see something as simple as one of the kinematic formulas that we use for constant acceleration, y equals 1/2 at squared. This is to solve for t. So all I'm asking you guys to do, you don't necessarily have to show all your work, as long as you're, for the sake of doing this packet, just to correctly solve for the variable that you're looking for. So I want t to be on the left side, so I have t equals. It's just generally how it's formatted. So how do I get t by itself? Alright, so I had the y over there on the left, so I've swapped sides. So to get t by itself, I have to get rid of the half. So it's being multiplied by a half here. So I'm going to divide both sides by a half. Now, instead of dividing both sides by 1/2, you can multiply both sides by 2. Okay, because technically you could all have also said that this is being divided by 2. So to undo division, you multiply. Either way, you get to this form. The next thing is that it's being multiplied by a, so I need to divide both sides by a. And then the last thing is that it's being squared, and so to undo the square, I take the square root. And so that is number 1, and that's what I would expect to see you guys do here. Let's do number 8 next. So 8, we see a formula that you guys won't actually use till the end of our class together, and that deals with the period of oscillation of various types of pendulums. You don't have to know this for the sake of doing this problem, because all I'm asking you guys to do is algebraically solve for one of the variables, and so in this case we want to solve for L. So in order to do that, what we need to do is first get rid of this 2 pi. So I'm going to have to divide both sides by 2 pi. And so what I'd have left over is the square root of L over G. And so now I need to get rid of the square root, so I'm going to have to square both sides. Okay? What I'm left with, having gotten rid of the square root, is just L over G. And so in order to get L by itself, I'd have to multiply both sides by G. And we've accomplished the task. We solved for L. You could further simplify this down. It's not necessary for this, but both top and bottom would get squared. So on the top, you'd have G, capital T squared, divided by 4 pi squared. And so that's fully simplified, but you didn't have to do that because all it asked you to do was to solve for L. Okay, let's try number 10. Now 10 has to do, the physics behind it, has to do with the focal length for various optical systems. And we don't cover optics in mechanics, but if you're going to pursue physics in any way, you will definitely see this at some point. But I'm asking you guys to solve for the DI here. So the first thing you need to do is to get this term by itself. So I would subtract this term from both sides. Okay. Now, right now, the last step essentially is to get DI into the numerator. So the one way you can do it is you can take the reciprocal of both sides, and so we use the exponent -1 to do that. Now, when you raise this term to the -1, what you get is DI over 1, or just DI. And so that has to equal this term right here, 1 over F minus 1 over DO to the -1. That's okay. You can leave it like that. The other way this could be written is 1 over 1 minus F minus 1 over DO. Now, because that takes the reciprocal, it puts this whole thing in the denominator, because this was over 1, so we've taken the reciprocal, we flipped those terms. But that's generally not a form that is often used. So if you wanted to simplify this any further, which again, you could leave it in the form that I have it here, is to first get this term here as to have a common denominator. So the common denominator would be FDO. So I'd have to multiply this side by DO over DO. I can that's like multiplying by 1, which you can do. And I have to multiply this term by F over F. And so by multiplying top and bottom, here by DO and here by F, you get a common denominator. So you get DO over DOF, or FDO, doesn't matter, minus F over FDO. And so you get that as the common denominator. Now, if you take the reciprocal, you can just flip these top and bottom. And that might be a form that is easier to work with. But again, for our purpose in just solving for DI, this is all you really needed to do. Okay, so if you have any additional questions, send me a remind, leave a comment below, and I can try to answer them for you. but we're going to move on to part 2 now, which is scientific notation, simplifying units. I'm not going to go over all the work, but for instance, I just want to show you, give you an answer, and that way you know what I'm expecting here. So for like number 1 in part 2, let's imagine we were looking for some period of time in this expression. You have some values that we had plugged into an equation. They have units. You can see that the value you have values to work with, so you're just plugging these numbers into a calculator and getting an answer. Now notice a number like 4.5 times 10 to the minus 2 kilograms. This is written in scientific notation, and it has 2 sig figs. All right. The number in the denominator, 2.0 times 10 to the third kilograms per second squared, also has 2 sig figs. So no matter what the calculator tells you, your solution should also be 2 sig figs. So what I get is 3.0 times 10 to the minus 2. And now you need appropriate units for this value. Now it should follow straight from the calculation, but if you know anything about period of revolution, that's a time, it should be in seconds. But let's just confirm that that's what you expect it to be. So we're going to do a unit analysis. So the units for the period, and when I do unit analysis I use these brackets. That's going to equal, you have a number, so that number, the 2 pi, has no units. So you start off with the square root, and on the top I have units of kilograms, and on the bottom I have units of kilograms per second squared. And so now we're going to simplify this down. You have a kilogram on top and a kilogram on the bottom. So they cancel. Now without simplifying just yet, I'll do an extra step here just so you can see what I'm left behind with is 1 over second squared. So improper fraction, that means I multiply top and bottom by the reciprocal of the denominator. I normally never go through the lengths of going through these steps in detail, but just so you can see that this is how it all works out. By doing that extra step, that gets rid of the complex denominator, and all you're left with here is the second squared on top. So you get the square root of seconds squared, and the square root cancels the square out, and you're left with seconds. So you go back up to your number and you put an S there. The period should have units of seconds. So that's what I'm expecting to see is our answers that take this form. Okay, let's take a look at what's next. Part 3, factor label method for converting units, and then carrying out various conversions. So here's what I want to see for this section. Let's look at number 1. This is a calculation that we've done quite a few times last year, but we want to find how many seconds there are in a year. So we start off with 1 year, and at the end of this process, we're going to figure out how many seconds there are. So you're going to get a number. The way we get from this side of the equal sign to this side is by multiplying our value here, our measurement, by factors of 1, and these are conversion factors that take the units that you start with and tell us what the units are that we want to end with. So you can take this in multiple steps. I mean, the whole point of this problem is to know how many seconds there are in a year. If you already knew how many seconds there were in a year, then there would be no point in needing to do this. But let's assume that you don't know. So you want to break down a year into units that you might be more familiar with. So what you'll do is open up a set of parentheses, place your division bar, and we're going to put together a ratio that has to be equal to 1. The numbers don't necessarily equal 1 when you do the dividing, but it's the measurements that do. Okay? So the other important thing is that if you're starting with, let's say, years, that's going to go on the bottom of this ratio because they need to cancel out. So I will erase this in a second, but just so you can see, years on top, years on the bottom, they would cancel out, and you're left with whatever units that you'd have up here. So we all should know how many days are in a year. So that might be my first step in converting. It's not what I want, but it gets me closer. So I know how many days there are in a year. If you want to be exact, we can say that's 365 and a quarter. And that's how many days there are in 1 year. So again, notice if without the units, 365.25 divided by 1 is not equal to 1. So you're in essence not, if you were multiplying that through in this problem, it would change the situation. It would change the math of what's going on. But this ratio isn't just a number. It's equal to 1 because the quantity 365.25 days is equal to 1 year. It's very important. So if we divide both sides by 1 year, on the left you get the ratio that we see above, and then this is equal to 1. You have the same thing on top and bottom, so they divide through and you get 1. So by multiplying our starting number, our starting measurement, with this quantity here, we are just multiplying by 1, which results in the fact that whatever we get after we do the math on this side of the equation, we know it's identical in magnitude to what we started with on the left-hand side. Right? You have to be thinking about it in this way for it to make sense. So that gets rid of the years for me. So now if I just multiply 1 times 365.25 days, I get 365.25 days. That's how many days there are in a year. I don't want that. I want to know how many seconds. Now, if you knew how many seconds there were in a day, then that would be what you could put into your next case here, your next ratio. But let's assume you don't know that either. So maybe another way to break this down is hours. How many hours are there in one day? So I want to put days top and bottom. Okay, so that's going to cancel the days out. And I'm going to replace that with, on the top I'm going to place hours. And so that's going to now convert my 1 year into how many hours there are in 1 year. And so the ratio is, I can tell you that there are 24 hours in 1 day. And you could then go into minutes and then go into seconds. But let me just jump an extra step here because I'm running out of room. And I can tell you that in 1 hour there are 3,600 seconds. 60 seconds in a minute, 60 minutes in an hour. 60 times 60 is 3,600. Let's just double check that all of our units canceled where they should have. Years are gone. Days are gone. Hours are gone. What I'm left with is seconds, and that's what I'm looking for. So I can just now multiply all these numbers through. There's no important numbers in the denominator. It's all 1. So everything that we care about is on top. So you get 365.25 times 24 times 3,600, and you get roughly 3.2 times 10 to the 7th seconds. Okay, so I'll let you guys work on the rest of those conversions. The next section is trig and basic geometry. I don't think I need to go over any of that stuff with you. That should be pretty straightforward. Let me know if there's anything that you would like me to go over. Part 5 is graphing techniques. You're just plotting the data. We're looking at what kind of graph you get, using the graph to determine the relationship. Go back to your notes from the beginning of last year to know all the different types of relationships that there are. I can tell you, I guess it would make sense to do it now. If you graph two variables, x being, again, the independent, y being the dependent, you can tell me what the relationships are between x and y depending on the shape of the graph. And I'll do them in different colors. So if you get a straight line, we know that that is a proportional relationship. Y is proportional to x. That means if I increase x by a certain amount, then y also increases by a certain amount. And that ratio doesn't change. This is your delta y. This is your delta x. And in a proportional relationship, delta y over delta x is a constant. And that's what we call the constant of proportionality. And in this case, we can also describe it as the slope of the graph. So if your graph can be represented with a constant of proportionality that doesn't change, it's a constant, then you have a proportional relationship. If then, I'll do another graph here. If we have a parabola, then this type of parabola, x is increasing as the square. So we would say y is proportional to x squared. So y gets faster than x does. So if I went up by certain amounts along the x axis, the rate that delta y changes by is not constant. It's a value. So there's hardly any change here in delta y. So if this was a straight line, then delta y over delta x would be a constant. But in this case, it's not constant, because if I take now that same interval somewhere later along the curve, so I'm going to try to get the space between this line and this line to be about the same. Okay, so this is supposed to be the same delta x. Now if you look at the change in y now, clearly has increased. The space between these two lines is greater than it was before. So now if I did delta y over delta x, since this number is bigger than it was before, this ratio would be larger. And I'll do it one more time just to show you. Again, we're going to cut this up into an equal slice here, so that I have not changed delta x at all. And now I'm going to go up to the graph, and I'm going to see how much y has changed in that same delta x amount. And you can see now that as we move to the right on our graph, delta y is increasing. So what we can tell by this relationship is not only that delta y over delta x is not constant, it's increasing. What we'll talk more about at the beginning of this year, when we get into calculus, is the fact that we can look at this type of relationship pretty quickly and determine that if we look at by how much this ratio is increasing, that we would learn for this type of relationship that it's increasing at a constant rate. Now, you would know that from our work that we did this year because of a formula like x equals 1/2 at squared. that is came from the relationship that x was proportional to t squared, and this 1/2 times a term was our constant of proportionality. But what it actually represented was the acceleration, and the acceleration itself was constant. The acceleration is the rate of change of the velocity. The velocity on a position time graph where you had x and t on these axes, when you get a parabola, the velocity is the slope. So if the velocity is the slope of this graph, the acceleration was how quickly the slope was increasing. So we'll get more into that as we delve into the topics from at the beginning of this year, talking about calculus. Another relationship would be this type of parabola. Right? So now what we get here is the opposite effect than what we did before. If we were to cut delta y up into little increments, we would see that delta x would be getting bigger. And so we can also use symmetry to make the argument that this relationship must be that y squared is proportional to x. And then the last relationship that you're expected to know is the hyperbola and here it's not a straight line, so it doesn't have a slope, but the ratio that a delta y decreases by is the same amount that a delta x would increase by. So that indicates an inverse relationship. So delta y is decreasing at the same rate that delta x is increasing. So that we would get y is proportional to 1 over x. The last section in this packet says how to choose the right graph for plotting. These type of questions often come up quite a bit in the free response section of the AP exam. You're guaranteed on your free response on that exam to have one question out of the 3 devoted to something that's sort of styled around an experiment. So it might ask you to design an experiment, to list materials that you would need to do, and then what kind of data would you collect, or they would give you data and you have to do some graphing and straighten the curve and find out relationships and determine meanings of slope. So being able to answer these last type of problems here is actually very important, and it goes a long way with what we'll be doing in this class this year. But let's take number 1, and just so you guys have a clear understanding of what they're asking for here. So we've looked at this formula before. Now, it says in part A, what variables should you plot against each other in order to prove that the period does not depend on its mass? Well, in this situation, there's no mass in the formula at all, so there can't be any dependence on mass if there's no m inside the expression. But let's take a look at what type of graph you would get by graphing certain quantities here. So let's put t on the vertical axis. Now, if I were to graph L, okay, so if I had collected data, let's say L was in meters, and the result was the period would be in seconds. So I knew certain lengths that I measured, and I would time it, and so I would see how much time it would take. What kind of graph would this look like? Well, you have to look at what else is in this formula. 2 pi is a constant, so there's nothing in the experiment that's going to affect 2 pi. Little g is our 9.8 meters per second squared. So as long as we're here on Earth, then I can do this experiment over and over. I can change the length of my pendulum, and that will consequently affect the period. But I know that I should get the same results each time. There are no other variables in the experiment that would mess up the time that I should get. Now, for instance, if I took the same length pendulum and I brought it to the moon, you might be under the assumption that if g wasn't a factor that we have to worry about, that if I have a certain length and I calculated here on Earth what the period should be, that if I swung the pendulum of the same length on the moon, that you might expect to get the same period on the moon, and that wouldn't be true, because now, even though L is the same on the moon, g is different, and if g is different, then t will be different on the moon. But here on Earth, I can run this experiment. If I measured a length L and I ran the experiment a dozen times, I should always get the same value for t, because there's no other variables that affect that experiment. Now, that's a pretty interesting conclusion, because you might think, well, there's a bunch of other things that could affect it. The mass, the length, the how high you swing it from, air resistance. I will say that this formula comes from a mathematical model, a physical model of a system that does not depend on air resistance. All right, so air resistance would change the total time that it takes to swing back and forth. That's not going to be visible in this form, so no air resistance, but you would be taking out air resistance. It would be interesting to know that the mass does not matter, nor does the height of the swing, as long as the angles remain pretty small. Now, all of that we will discuss in detail later on in the year. Right? But here on Earth, with little g being 9.8, you realize that little g is a constant. So I can essentially pull that out front. How do I pull that out front? Well, again, I don't normally go through all these specific details, but I can split the square roots up into 2 pieces, top and bottom. So that's identical. and I can just shift this guy over to the left here. It doesn't matter, because this whole thing, that's what it looks like. It's 2 pi times square root of L divided by square root of G. So I can make it look more like this. And that's the same thing. But what you see in this form is that this is just a constant. So if that's true, then t must be proportional to the square root of L. Okay, because we know that if we were to go backwards, if I wanted to go back to the expression, that I'd have to replace alpha with an equal sign, and then I need some constant of proportionality times our other variable, square root of L. And in this case, what k would be is 2 pi over the square root of G. You get back to the original formula. But now, knowing that this is the relationship, you can make a prediction about what the shape of the graph will look like. If this is t and this is L, a t proportional to the square root of L, well, what's y equals square root of x? That's the over curve. So this could also be rewritten as t squared is proportional to L. That would also be appropriate, but your constant of proportionality would have changed a little bit than what we had defined it to be up here. Why is that? Because to go from, we've established k to be this from this form. If I square everything, then I have to square k also. So let me just say one other thing about this. If I wanted to produce a straight line, what would I need to graph? I'm putting t, keeping t up here on my y-axis, and square root of L, should have units of square root of meters, on my x-axis. I would get a straight line, and the slope would be k, where k is equal to 2 pi over the square root of G. That follows from exactly what we talked about up there. Now, I told you last year that I hate using square roots on my graph. This would be an exception because of the way we put it together. Things make sense, but we could get rid of the square roots, but your k would be different. What the slope would tell you is not this quantity here. If we plotted instead t squared, I would have units of second squared, and then L in meters, you would definitely still get a straight line, because these two relationships tell the same story, but the constant of proportionality is no longer k, it would be k squared. Right? That follows from this form. If I want to get rid of this square root, I got to square everything, so k gets squared. So what I get for k would be 4 pi squared over G. So think about that. What could we use this data to obtain? Well, here I am finding using different length pendulums. All right, so there are various different lengths, and then I've taken the time that it takes to swing back and forth, and I've squared those values and I plotted them against the length, and you get a straight line that produces a slope, which is equal to this quantity right here. So I get, in this case, that the slope, the actual value I get, if I did lin reg on my calculator, I get a slope. That equals 4 pi squared over g. Let's say you were on a different planet and you didn't know what little g was. You could quickly do this experiment, measure different lengths, time it, find the slope of this graph, t squared versus L, and by finding the slope, you can solve this expression for little g. Little g would just be 4 pi squared divided by the slope. And that would be one way of calculating what little g should be. Now, interesting also, the slope should have a unit, and you can figure out that by doing a unit analysis here. What units should the slope have to make this side equal to meters per second squared? So if I solve for my question mark here, I get 1 over meters per second squared. That's the same as seconds squared per meter. So my question mark bracket here, that's my slope units, have to be seconds squared over meters. Okay. And then the last section, you're looking for trying to explain. The gradient is just a fancy word for slope. So if you look at the table that you're asked to fill out, let me go over one that they already gave you just so you know where those answers came from. So they give you an equation. The first two rows deal with what we call is Ohm's law, which deals with electricity. R is resistance, V is voltage, and I is electrical current. It says plot Y against X. Okay, so we're going to place, this is our Y-axis, this is our X-axis, and we're saying that on the X-axis we're going to put current. And then on the Y-axis we're going to put voltage. Now, based on this relationship here, what type of graph would you get? And we're going to assume that these are all going to give us straight line graphs, because the gradient, you can only find the gradient of a straight line that's not a function of something else. It's a constant. So I want to rearrange this equation into a form that gets v on one side and I on the other. Alright, so I'm going to multiply both sides by I, and then I'm just going to flip them around. So I'm going to get v equals I times r. That's often the way it's shown, but you could have easily rewritten it as r times I. And either way, if we were to graph v on the y-axis and I on the x-axis, then r must be the slope, because that's as long as the resistance is constant, then v would be proportional to I, so you'd get a straight line, and the slope would have to be equal to this resistance. Skip to the third one down, where we have capital E stands for elasticity. But it's also referred to as the Young's modulus. And they gave you an expression, F over A divided by X over L. And they say L is a length, X is an extension. That's like when we talked about springs. If we stretched a spring by a certain amount, then we usually call that X, or delta X. That's an extension. And that's, even though this extension happens in the y direction for this example, we might still call it X, because X is just short of extension. So, but it says now to graph on the x-axis force and on the y-axis the extension. So I'm going to graph extension on the y, force on the x. And I want to rearrange then this expression, because this expression tells me how all of these different variables relate. And I'm also going to assume that this is going to produce a straight line for me. So that's going to fix all these other variables to being constant. But let's first off simplify this down. So I multiply top and bottom by the reciprocal of the denominator. That gets rid of this, and so I get FL, so E equals FL over AX. And now I want to get X onto one side, keep F on the other, and again, if you want a graph like this, you want it to get into a form as y equals m times x, right? So that way, whatever is in parentheses, that's the slope. So, for instance, I could multiply both sides by ax. That satisfies what I just said, that I put x on one side and kept f on the other. But the issue is it's not in this form, because you want the dependent variable y to be by itself. X can be multiplied by a constant, and that constant would represent the slope. So I kind of have to undo a little bit of what I just did. I didn't have to multiply a to both sides. I could have kept a by in the denominator there and just multiplied both sides by x. But since I already did it, now what I'm going to do is I'm going to divide both sides by EA. Okay? So what I get now is that x equals something times f. That's the form that I want. What that something is everything that's left over here. Alright, so we have L divided by E times A. So the slope, or what this paper says is the gradient, equals L over EA. Now, if you were interested in determining with this information what the value of E is, so assuming you know what the length is, you know with A, which is the area, surface area of the object that's being stretched, we're looking at its elastic properties, and you know what the slope of this graph is, you can rearrange this to find E, which is easy. I can just swap E and slope, and I get that E equals L over the slope times the area. And so you'll see on your paper Young's modulus, length over A times the gradient. That's the same thing as this. Okay. So I hope that helps you understand some of these mathematical concepts a little bit more. These are things that with work it becomes a little bit more intuitive, but really, really important skills to have in order to understand the physics of what's going on. You know, our goal is not to just simply do math, but to understand what the math is telling us about our system. And so if you're looking for certain properties, you should know how to manipulate mathematical quantities in your expressions so that you can find out more about the things you're interested in. So what I'm going to do is I will create a part 2 of this video that will go over the physics material on the next packet.